Hello everyone, welcome to this presentation about project Selinon, about dynamic distributed computing that Selinon offers you, and it will be a dynamic distributed computing using popular programming language that is Python. So let's do some distributed computing. In this section I will use terminology as used in project Celery, so if you are familiar with Celery, feel free to skip this introduction. In Celery we have something that is called a message. This message carries information on what should be computed. It does not carry information on how the given thing should be computed. So you can imagine a message being a JSON that is published on some message broker. A message broker is basically a service that queues messages, incoming messages, and offers these messages to workers that are connected to it. So we have workers connected to this message broker. And if we have available worker that knows how to process the given message, it picks the given message and starts to processing it. Meanwhile, there can be queued more and more messages, and if we have available workers, an available worker picks some particular message and starts to processing it. In Celery terminology, we have something that is called a result backend. This result backend stores results of computed or processed messages. So once worker 3 finishes processing a message, it writes results to result backend and becomes available to process another message. Meanwhile, worker 1 also finished processing the given message and stores result in the result backend. This is basically a really high-level overview on how Celery works. Celery is quite popular Python project available out there. It's open source and it's one of the largest Python projects or open source Python projects available out there. Celery is an implementation of distributed task queue, and you can find it in many open source projects, for example in Django Celery or in Sentry monitoring system for background tasks. Okay, so let's use Celery to do something like task flows. So I didn't mention, but a task is something that processes the given message. So let's create some task flow. So we have these tasks, namely task 1, task 2, task 3, task 4, task 5 and task 6. And we have these dependencies between these tasks. These dependencies could be data dependencies, so if you would like to run task 5, you need to run task 1, task 2, task 3 first, and then you can proceed to task 5 that probably reuses or computes other results based on results of task 1, task 2 and task 3. So we have these data dependencies, but we can also have time dependencies. So, for example, you cannot run another task before some task. So, what we can do? We have these tasks, and we can create some kind of master task where we put implementation of all of these tasks into one giant task that, in this case, processes message and runs task 1, task 2, task 3, task 4, task 5, task 6. Okay, this is doable, but it's not that nice solution. Why? Because ideally we would like to run task 1, task 2, task 3, task 4 all in parallel, possibly on different worker nodes, so also possibly on different cluster nodes in our deployment. And once all of these 4 tasks finish, we would like to proceed to task 5 and task 6. So we can do it using something that is called Celery primitives. This is something that Celery offers us. Celery offers primitives such as groups or chains and many others, but basically what they offer you that you can run one task after another, so you have some task chaining, but you can also group tasks and run all tasks stated in a group in parallel. Okay, so let's do it. So we have this initial flow design and we create something like phases. So we put task 1, task 2, task 3, task 4 all into one phase, and let's call it phase 1. After phase 1 finish, finishes, meaning all tasks in this phase finish, we proceed to phase 2, where we run task 5 and task 6 all in parallel. Okay, so we have this flow design. This is doable in Celery. You create this flow, you state it in your source code, and then you realize that you would like to add a new task. And you would like to add a new task called task 7 that has a dependency on task 2 and task 6. Well, how to do it? One approach is basically to create phase 3 and put task 7 into this phase. Another approach is to put task 6 into some phase 1.5 and then put task 7 into phase 2. Well, it depends what solution is best, and it depends on task time execution. So it's not that straightforward to answer how to do it. Okay, so let's take a look at time execution of tasks. So in our initial flow design with these phases, we found out that task 1, task 2, and task 4 and task 6 all finish in 1 minute. Then we have task 3 that finishes in 30 minutes, and then we have task 5 that finishes in 10 minutes. Okay, so if we have this phase, basically we block execution of next phase based on the longest running task in our phase. So in the first phase, we could basically continue to task 6 after task 2 and task 4 both finish ideally in 1 minute. So we get results of task 6 in 2 minutes ideally, but we are blocked by task 3 that takes 30 minutes to execute. So we get results of task 5 and task 6 both in 40 minutes. That is not nice if you would like to have a responsive system. Okay, so let's remove these boundaries, and we get results of task 6 in 2 minutes ideally, and results of task 5 in 40 minutes because it's on the path of longest running tasks in our flow. Okay, and if we remove these boundaries of phases, boundaries that created phases, we can easily add a new task because we don't have to bother with some phases. We just state, okay, we would like to run task 7 after task 2 and task 6 both finish. So if you use Celery for this flow design, it's not that straightforward to add a new task, and if you are adding a new task or removing tasks, you can easily break the initial flow design. You have to document how the flow behaves, you have to handle different use cases, and you handle all of this in your source code. That is not nice. You can easily introduce a bug, and all the logic is hard-coded. And then you might be thinking, okay, and what about task failures? Celery offers you something that is called retry mechanism, where you can retry the given task. But what if retrying the given task is not enough? What if you would like to run some fallback scenario if some task fails? Or you would like to run some fallback scenario if wall flow fails? And what about reusability of task implementation? You have basically the wall flow hard-coded into your source code. And what about using different storages and databases? In some cases, you have relational data you would like to put into a relational database, for example, Postgres. And in some cases, you have key value data that you would like to store, for example, in Redis. And in other cases, you would like to query some graph database that has or that states different dependencies or graphs in your computed data. So this is not that straightforward with Celery. You need to create some library and handle this on your own. Okay, so these were the core ideas, or these pitfalls led to introduction of Selinon, and Selinon means celery in Greek language. Its main aim is to create a YAML configuration file that separates task flow logic from task implementation itself. It creates this flow abstraction, flow of tasks, and it allows you to model graph of dependencies, and you can do various things like assigning different storages to different tasks. You can run tasks, you can run flows, you can run nested flows, you can evaluate some fallback scenarios, and so on and so on. So let's take a look at it. Let's consider that you would like to compute results, and you would like to compute or multiply numbers A and B that are stated in the message you published on message broker. So in Selinon world, you derive from Selinon task and you provide the run method, that is the entry point of the task implementation, and you accept these node args that are basically a message that is published on a message broker, if you put it very high level, and you multiply numbers A and B, you store it in the result variable, and then you return a dictionary, and this result is available under the foo key. Okay, so this is task implementation. As you can see, you don't bother how you store results. The only thing you state in task implementation is basically how you compute results. Okay, so we implemented this task, and next thing to do is to register task in your YAML configuration file. So in the YAML configuration file, under the tasks section, you register your newly created task 1, and you state the name of class, and you also state import from where it's a Python package or Python module, from where Selinon should import this task. If you register all your tasks under the task section, then you provide flow definitions section where you state basically flow of tasks. So in this case, we created a flow that is named flow 1, and you provide edges that are basically transitions between these tasks. In our case, we created 2 edges. The first one leads to task 1 and has no source or from stated or from task, meaning that's the starting edge of our flow. So we start with task 1. After task 1 finishes, we run task 2 and task 3 in the second definition of our edge, and both tasks 2 and task 3 are run in parallel. Okay. So we create this YAML configuration file, we plot graphs, we can use Selinon directly, use Selinon CLI directly to plot graphs of our tasks or of flows of our tasks. And in this case, we have this flow, and as you can see, we start with task 1, and after task 1 finishes, we run task 2 and task 3 all in parallel. Okay, and we have these octagons, and these octagons state true in them. What are they? They are basically conditions. Conditions is something that allows you to behave conditionally based on some external or internal events, and conditions are basically Python functions. You can directly implement your own, plug them into Selinon, and these Python functions return true or false based on some events you would like to check or track. So let's create a condition. So in our edge definition, we provide the condition key, and we proceed from task 1 to task 2 and task 3, meaning we fire edge from task 1 to task 2 and task 3 if field is equal. The result of task 1 has field proceed, key in dictionary, and this key is proceed, and the value of this key is yes. This is field equal check. And then if that is not true, we also check precedence of an environment variable, and if environment variable named testing is set in our deployment, then we proceed to task 2 and task 3. So this condition can be grouped using Boolean operators such as or, and, but there is also supported not. These conditions are made of predicates, so field equal and exist are predicates that return true or false based on checks they perform. Selinon also offers some predefined predicates, so you can directly use predefined ones. Okay, so we have this flow, we have condition stated. So if we plot our flow, we get this graph, and we can see that we have this conditional execution of task 2 and task 3. Okay. You might be wondering, okay, we put this condition, but where results of task 1 are stored? And the answer is storage or a database. Selinon creates abstraction on top of storages and databases and provides you predefined storage and database adapters, but you can implement your own. So for demonstration purposes, let's create one. To create a data storage adapter, we simply import data storage class, and we derive from it, we implement abstract methods like connect, retrieve, store, and we implement our storage adapter for Redis, and we provide information on how to connect to this database, how to retrieve, and how to store results. So we are the owners of the logic, how we structure data in the database or storage to later support querying and so on. So this is implementation of a storage or database adapter. Once we implement the given storage or database adapter, we just register it in the YAML configuration file under the storages section. So in this case, we put Redis in the storages section. We provided the import or package or Python module from where the given implementation should be imported, and we provide also configuration like host, port, user, and so on, how needed for connecting to database. So this configuration is passed to database adapter or storage adapter constructor by Selinon transparently. And then when we would like to use these database or storage adapters, we just assign them to tasks. So tasks solely have the implementation on how to compute results, and then we have these storages or database adapters that state how results should be stored in databases or storages we use. If we visualize this configuration, we can see that the results of task 1 are stored in PostgreSQL, and results of task 2 are stored in Redis. Results of task 3 are discarded if there are any. Okay, nothing is ideal, and there are errors and failures in a real world. So let's tackle them. Selinon offers you to tackle for task failures and also task or flow failures. I will talk about it briefly. So imagine we have our flow definition, and we would like to run some fallback scenario if task 2 fails, but we also expect, or we would like to also handle a case when task 3 fails, and we would like to handle it differently. So if task 2 fails, we would like to run fallback 2 task, and if task 2 and task 3 fail at the same time, we would like to run fallback 1 task. You might be wondering, okay, but if task 2 fails and task 3 is still processing, what fallback would be run? In this case, Selinon waits for tasks to finish, and if task 3 fails, fallback 1 is run, and if task 3 succeeds, fallback 2 is run. So there are no time-dependent evaluation of failures in Selinon. Okay, if we plot the given fallback scenarios, we can see that if task 2 fails, we run fallback 2, and if task 2 and task 3 fail at the same time, we run fallback 1. With new version of Selinon, you can put also conditions on these failure edges, so you can put your own condition under which fallback task should be run. It's also worth to state that once you run a fallback, you can return to normal execution of your flow based on your configuration. So when you provide that you would like to run, for example, task 4, once fallback 2 finishes, you can do so just by putting the configuration section in or edge configuration in the YAML configuration file. Okay, now Selinon offers also subflows or nested flows. What does it mean? It means that you can run a flow from within a flow. So basically, Selinon does not strictly distinguish between task implementation or task in the YAML configuration file and the flow definition. So basically, tasks and flows create nodes in the YAML configuration file. That's also why you put a name for YAML, for flow definition, sorry. Okay, so in this case, we run some init task as a first task because there is no from task or from node stated. And once init task finishes successfully, we run a nested flow 1 based on the configuration in the YAML configuration file. And once the whole flow 1 finishes successfully, we run task 2. It's worth to state that errors or failures in flows are propagated just like exceptions in modern programming languages. So if some task in flow 1 fails and there is no fallback scenario stated in the YAML configuration file, the whole flow is stated or is marked as failed, and this failure is propagated to parent flows if there are any, and you can basically catch failures of nested flows in parent flows as well and handle them. Okay, so this is like very brief overview what Selinon offers you, and you might be wondering, okay, how does Selinon work under the hood? So the key idea is in dispatcher task. It's basically a scheduler that periodically, based on your YAML configuration file, checks the state of flow, and based on your YAML configuration file, it schedules new tasks as stated or respecting your YAML configuration, and it provides flows to these tasks and nested flows. So you can see Selinon flows to be flows of tasks or flows of flows or flows of arguments, or if you group tasks and flows together, you can see it as a flow of nodes. Then Selinon offers you this YAML configuration file abstraction, so you have the ability to do or to reuse different flows and tasks, implementations, and also an important feature of Selinon is a system check. So if you change something in your YAML configuration file, Selinon does checks for you, and based on these checks, the whole deployment or redeployment of your system can fail. So you are sure that you have always working system based on your declarative YAML configuration file. Selinon also offers you flow visualization, so if you have different flows, you can visualize them, and it's easy to inspect like how your cluster behaves based on these visualizations that Selinon offers you. Basically, all visualizations in this presentation that were from YAML configuration file were created using Selinon CLI. Okay, so let's have a look how Selinon or dispatcher runs different tasks in time. So let's say we have this flow, and this flow is made of task 1, task 2, and task 3, and we have these dependencies, air data or time dependencies on tasks. So we would like to run task 3 after task 1 and task 2 finish. So at the given time, at time 0, we request it to run this flow. Ideally, at this time there is also scheduled and run dispatcher. It's worth to know that there is one dispatcher per flow. So if you run a nested flow, there is created a new dispatcher that handles the nested flow. So at the given point of time, at time 0, Selinon knows that this is a new flow, and you request it to run task 1 and task 2. So Selinon schedules these task 1s and task 2, and possibly different worker nodes in your cluster pick these tasks and start to processing them. As these tasks are not final tasks in flow, Selinon retries, and it retries in 5 seconds in this case. After 5 seconds, Selinon checks the state of task 1 and task 2, and it sees that both tasks, task 1 and task 2, did not finish. So it retries after another 5 seconds. So after 10 seconds, we have another dispatcher check, and we see that task 1 finished. But respecting our YAML configuration file, we see that if we would like to proceed to task 3, we need also task 2 to be successfully finished. So Selinon retries after another 5 seconds. So after 15 seconds, we see that task 1 and task 2 both finished. So dispatcher schedules task 3 and retries after another 5 seconds. This is basically the idea of how Selinon works under the hood, and you can see the dispatcher task as a scheduler that basically periodically samples the state of your flow, and based on your YAML configuration file schedules new tasks or new subflows respecting your YAML configuration file. There are also other features. Worth to state are probably caches. So if you would like to optimize network traffic in your cluster, you can do some distributed caching. I will talk about it later in this video. You can do also task and flow throttling or prioritization. You can do it naturally. So if you have more workers that serve some tasks, you basically prioritize because you have more workers that can process more tasks in parallel. But you can do also flow throttling, so you put less workers that process some tasks. But Selinon also offers you throttling in the YAML configuration file, where you can throttle or where you can state, I don't want to run the given task or given subflow more often than, let's say, 10 times a minute because of some remote API throttling, and I don't want to reach this remote API throttling, so I throttle on my side. You can also do retries if retries on task level if you would like to do so. It's also another possibility how to do that. There's also a mechanism on optimization of dispatcher scheduling, so you don't need to retry dispatcher after 5 seconds, but you can do something like exponential backoff, or you can register your own function that basically returns time after which Selinon should retry. And this is some kind of optimization of dispatcher scheduling. So if you have a long-running task, you can say, okay, now I don't want to retry dispatcher after 5 seconds, but rather after 1 minute, because I know that that task is some long-running task. So it's optimization of my cluster as well as dispatcher scheduling. Selinon also offers you trace points, and these trace points are some significant or worth to state events in your cluster. So it could be, for example, a flow has started as dispatcher is read-write and checks status of your flow, but it's also, for example, that task started, the task finished successfully, that task failed, or the whole flow failed, and so on and so on. You can find all of them stated in documentation. These trace points are well structured, so when you do aggregated logging and you have deployed elastic log/kibana, you can automatically aggregate these logs from your cluster, and you can explicitly tell Selinon in the YAML configuration file to report JSONs. So these JSONs are automatically aggregated, parsed on elastic log/kibana stack, and you can basically reconstruct your flow, how it went, what went wrong, if you would like to do debugging, or you would like to inspect how your flow behaved. You can also do something like migrations. So imagine you have running deployment and you change something in the YAML configuration file, how you would like to tackle it in your production system. I will talk about it also later in this video. Then there are selective task flows, where you basically replay a flow, and I will talk about this as well. Selinon offers you a CLI tool that is easy to access, CLI, where you can visualize flows using these flow graphs. But you can also do something like simulation. So you can run the whole flow on your laptop, simulating how the cluster would behave. Then there is a for each mechanism. This for each mechanism is basically something like I would like to schedule n tasks or n flows, and this n is determined on runtime. So I'm not sure now, when I'm scheduling the flow, how many subflows or tasks I would like to run, but you can register a for each function, and Selinon will iterate over this function and scheduled tasks or subflows that are run all in parallel, and this is all determined on runtime in your system, so your system is self-behaving. It's also worth to state that the CLI tool does migrations for you, but I will talk about it later. There are also other features. You can find them in the Selinon documentation. Okay, so let's have a look at migrations. So imagine you have a running production system. It respects your YAML configuration file, and then you realize, okay, I have this flow definition, I run init task, but after init task, I don't want to run flow 1 actually, but I would like to run task 3 for some case. And after task 3 finishes, I would like to run task 2, so I'm basically replace flow 1 with task 3. What can I do? With Celery, you can deploy a new version of your system aside of your old running system. If you don't want to clean or pure queues of messages, but that is obviously not nice, because if some users wait for messages to be processed, you don't want to clean them. So ideally you deploy a new version of your system that respects the new configuration, and you let the old system run and process messages that are already queued. Okay, you need resources for this, and you need overhead. So you create new queues, you adjust your, for example, API server that publishes messages on message queue to publish it to queues that on which new workers with new configuration listen on, and it's not nice. So Selinon offers you this migration feature, and this migration basically is a generated file that states how Selinon should migrate old flows. If you have old system running and this old system already started flows, in this case flow 2, and it already started flow 1, and then suddenly you do redeployment, how should Selinon work? So this is something that is called a tainted flow. That is a flow that would behave with new configuration differently compared to the old configuration, and these tainted flows can behave based on tainted flow strategy. That is, they can be retried, so Selinon reschedules the whole flow and recomputes results of tasks and possibly subflows, or you can ignore it and let the system run with the old configuration, or simply you can mark these flows as failed because they don't respect the new configuration. This tainted flow strategy is up to you, and it's basically how you would like to tackle these tainted flows. So it depends on your case. Okay, now let's discuss these selective task runs. So you have a YAML configuration file where you declaratively put how your cluster should behave, and you would like to run only some particular task respecting the configuration. So we have this flow, and we would like to run only task 7. We don't care about results of other tasks, so we would like to refresh results of task 7 because, for example, task 7 is some task that captures some data that vary in time. So task 7 samples something. Selinon offers you these selective task runs. So the only thing you state that I would like to run only task 7. And Selinon automatically computes which tasks should be run respecting dependency graph. So task 2 and task 6 are direct dependencies for task 7, but there are also task 3 and task 4 that are direct dependencies for task 6. So Selinon runs task 2, task 3, task 4, and task 6, and then it proceeds to task 7. Task 1 and task 5 are not run. You can also optimize this selective task run, and you can provide optionally a function that tells Selinon from where results for particular tasks should be retrieved. So you can state, I don't want to run task 6 again, but rather I would like to reuse results of previously computed results that were previously computed, and the same can be done for task 3, task 4, task 2, meaning if you would like to refresh only task 7, previous results of task 2, task 3, task 4, task 6 are retrieved from database or graph or from whatever storage or database you use, and the only task that is run is task 7 as you requested. Then there is something that is called distributed caches mechanism. So you have workers deployed in your deployment, and if you would like to optimize network traffic in your cluster, you can do so by deploying aside caches. So for example, you can deploy Redis in the same pod as worker is. And you can cache results, or Selinon will transparently cache results for you. Actually, there are two types of caches. One is the cache for actual worker results. So if you compute results, these results are stored in cache, and later in, for example, conditions, these results can be reused. But there are also caches on state of tasks. So you can put or cache results of task states there, and these states are something that is persistent. And if you know Celery, that is also the reason why the result backend is still present even in Selinon. So Selinon or Celery puts states of tasks into result backend, and these states are used by Selinon to check the status of tasks. Okay, so to sum up, Selinon is currently built on top of Celery. It uses Celery's logic for scheduling tasks and storing results of or states of tasks. But as you can see, it's not tightly bound to Celery. So possibly Selinon in the future can support other backend solutions, not only Celery. You have a simple YAML configuration file where you state how your flow or how your system should behave, and you have these loosely coupled components that are glued using the YAML configuration file. So you separate task logic from actual storing logic, from retrieving results of tasks, and the whole system is much cleaner, and you can reuse all components based on your needs. You have this conditional task execution that is an optimization as well as abstraction. So you don't schedule tasks that shouldn't be scheduled. So your deployment acts or behaves dynamically. But it's also an optimization for tasks that shouldn't be scheduled. You don't schedule these tasks. So the scheduling overhead is not there. Selinon offers you this flow abstraction, so you have tasks that are grouped into flows, and you can use different storages and databases based on your needs. So if you have some relational data, you can use Postgres. If you have key value data, you can use, for example, MongoDB for your documents, and you have this separation and the wall deployment or wall configuration is the truth for your cluster behavior. You have this advanced task flow, failure handling with fallbacks that can be fallback flows or fallback tasks, handling different scenarios. And Selinon also offers diagnosis using trace points, or you can directly use Sentry monitoring system. And in this Sentry monitoring system, you can track task failures. So if a task fails in your deployment, you can, or Selinon will automatically report this to Sentry. So you have error tracking system support built in Selinon. Here is a visualization of flows. It's worth to state that Selinon offers you like very high level abstraction, so you can build really complex systems using Selinon, and you have this ability to visualize how systems behave. You have this ability to inspect how they actually behaved in your deployment, and you can create very complex system using this high level Selinon abstraction. My name is Fridolin, and this was basically presentation of project Selinon. You can find Selinon on GitHub under Selinon organization, and hopefully you liked Selinon. If you liked it, feel free to put or give me star, and I thank you for your attention and looking forward to your ideas. Feel free to open issues in case you have some idea how to improve Selinon, or you can directly participate on development. Any PRs are welcome. Selinon is shipped under, I think, MIT or BSD license, so feel free to use it for whatever you would like to do. Thank you, and see you next time.